In this video, we're going to talk about stretches and compressions when we're looking at transformations of functions. So I'm going to do this by example. This came out of the book. So suppose P of T models growth of population of fruit flies, and that's this graph that's being shown here. And then let's say a scientist is looking at another population, but they start twice as large. But they're going to follow the same growth pattern, which basically means the whole time they're going to be twice as large as P of T. So they created this equation to express the second population, Q of T, and it's 2 times P of T. P of T are the outputs, so it's basically taking every output and doubling them. So let's see what that looks like then. As a graph, this is what Q of T is going to look like. Instead of starting at 1, it's starting at 2. And then you could see that the key points that we kind of look at for this first graph here, right at 3, it has an output of 3, 6, it has an output of 2. Here, it's doubled, right? At 3, it's an output of 6. 6 is an output of 4. So it's doubling all the outputs. And it's kind of has the same visual as the first graph, but it looks like a stretched out version of the first graph. And that's what vertical stretching and compressing does. Okay, so let's write that down then. So given a function f of x, we define g of x to be k times f of x. And k is representing a constant that is going to vertically stretch or compress f of x. And here's how we know which one it'll be. If k is bigger than 1, so it's like a 2, like the one we saw, the graph is going to be stretched. If k is less than 1, but not negative, okay? So because negatives means it's reflecting. So k is between 0 and 1, like a fraction, like a 1/2. That's going to compress the graph. And then, of course, if k is less than 0, that's when we see the reflection, which is why we didn't want to include that in the second one. Okay, and it could have a stretch or compression, depending on the value of k. So let's go ahead and look at what that does in the table examples that we have been doing. So if we're looking at g of x equals half of f of x, that means we're taking the output values and we're going to cut them in half. So same inputs. Let me go ahead and just do it right next to it since I didn't give myself all that much room. Oops, let me do that in a different color. Okay, so the input is 2. That means that the output is going to be half of what f of x is. So half of 1 is just actually half. For 4, the output then is going to be 3 halves. For 6, the output is going to be 7 halves. And for 8, the output is going to be 11 halves. So I'm just cutting all of the outputs in half. This particular example, none of them went in nicely. But sometimes they will go in nicely and they'll be whole numbers. Okay, so let's look at this example. This example, sorry for my dog in the background. In this example, we're given a graph and we're told to relate it to x cubed, which makes sense. It kind of looks like x cubed. But the graph of x cubed, and I would again recommend that you have these memorized. It goes through 0, 0, and then it goes through 1, 1, -1, -1. So it kind of goes like this. So already I see at 1, 1 over here, it's not going through 1, right? I'm sorry, at 1 over here in the input, the output is not 1. It's a fraction. Okay, so I already know this is going to be a compression. Normally it goes through 2 and then it goes to 8 and then -2, -8. But this graph, so that's normally what it looks like. This one at 2, it's going to 2. And at -2, it's going to -2. So normally we would be going, the input would be 2, 8. But this one is actually 2, 2. So the output then has been divided by 4. So that means then that this new function, g of x, is 1/4 of f of x. And that makes sense when I'm looking at the values of 1, right? I mean, that definitely looks like less than half. So being a fourth makes a lot more sense in terms of a compression. Okay, now it's possible to affect the input values. And that then is going to kind of change the way we look at this. So let's look at how a horizontal stretch or compression works. Instead of K being multiplied by the output f of x, K is going to be multiplied by the input x. So it's going next to the x. This is going to give us a horizontal stretch or compression. Now, kind of like how horizontal shifting does the opposite, that's what happens with the horizontal stretching or compressing, opposite of what you expect. When K is bigger than 1, it ends up compressing the graph. We get a compression, so it's compressed. When K is between 0 and 1, a fraction, it ends up stretching the graph horizontally. And then, of course, if it's negative, then we end up getting a compression or stretch, but also a reflection as well. Okay, so let's go ahead and see how that's going to kind of work in a table. So this time we have to adjust the output values. I'm sorry, the input values, not the output values. The output values we want to remain the same. We want to get the same outputs, but we need to figure out what inputs are going to give us that for g of x. So I'd like g of x to produce the same outputs. So to get an output 1, do that in red, an output of 1, I need to figure out what I have to input. Okay, so according to f of x, if I have an input of 2, I get an output of 1. So that means that for g of x, in order to get an output of 1, I need to figure out what I have to plug in here for x so that I get f of 2. So that means I need to plug in 4. So plugging in 4 is going to give me f of 2, because 4 times a half is 2, and that comes out to a 1. So g of 4 is going to give me 1. So I want to kind of do that one more time, and then we're going to use a pattern to finish. So in order to get out 3, okay, I need to plug in to do that. So f is going to give me 3 when it's a 4. So in order to get a 4, I have to put in 8. So g of 8 is going to produce 3. So basically what I'm doing is I'm having to double the input values in order to get the same output value. That's what we're doing. So it's going to be, instead of 2, 4, 6, 8, it's going to be 4, 8, 12, and 16. And that's going to give us the same outputs as f of x. Okay, so let's look at an example with 2 graphs, and let's figure out the relationship between them here. So we can kind of see that g of x looks almost like a squished version of f of x, and it's squished horizontally because you could see that the output values are exactly the same, right? The highest value is 4 for both graphs. The lowest value is 0 for both graphs. So the inputs are what has changed. Therefore, it is compressed horizontally. And what we want to do is we want to figure out what the compression is. That looks like a very sad Z. Let me fix it. Horizontally. There we go. It's compressed horizontally. So we need to figure out how to find that compression. So let's look at the first graph. On the first graph, I see, let me kind of look at this top point here, that occurs at 4, 4. That same top point here is not occurring at 4, 4. It's looking like it's occurring at, oh man, don't think it's maybe 1 1/3. Maybe I picked a bad point. Let's pick a better point. Let's pick one that's going to come out nice. So here, I see, I'm going to use the second graph to help me do that. I see that 1 has a nice output, right? See that? So 1 here, it's 1, 1 on the first graph. But on the second graph, it's 1, 3. Oh, let's pick some other points. First graph, 2, 2. I should probably do them in the same color, right? First graph, 2, 2. Second graph looks like 2, 4. So what I'm wanting to do is match output values. I'd like to have the same output to kind of help me figure it out. That's what I need to do. And right now, none of my outputs match. So let's try to match them up as best we can. I'm thinking, since these are the values for G, I should try to find those same output values on F. So I see that where F equals 3, that happens at 3. So let me match that one up. 3, 3. When F equals 4, that happens at 4. It also happens again, it equals 4 at 6. Now, the reason I'm thinking that might be more important is I'm trying to find a relationship between them so that it makes sense that they're the same. So here's what I'm looking at. For this first one, F of 3 equals 3. For G of 1 equals 3. Here, I'm going to look at this last one. F of 6 equals 4. But here, G of 2 equals 4. So what I'm trying to see is the input values. That's a 3 and that's a 1. That's a 6 and that's a 2. And I'm thinking then that this is probably not the better input value to use. Those two seem to have a relationship that I can kind of see. It looks like G is taking a third, right? It's 1/3 of F. What that means, though, in terms of a compression, is it kind of goes the opposite. G of X equals F 3X. So whenever I'm plugging in a value for G, it's getting multiplied by 3, and then it's going to have the same output as F. So it's kind of doing the opposite. I'm, instead of doing a 1/3, it's because it's next to the input, I'm doing a multiplication by 3. So that would be relate the two. But what it is it's actually compressed horizontally by a third. That's what's happening. And it makes sense because look at the last value, the last input value for F of X is 6. But the last input value for G of X is 2. That's a third of the size. So it kind of makes sense that this would have been the better way to have kind of looked at it, I think, is to look at the maximum inputs. But it's good for you to kind of see how I thought through that because I'm not perfect. All right, let's try an example that does multiple transformations, including some of the ones we just discussed. So for this one, they're asking us to do a horizontal compression of 1/3. That's the 3x. Then a stretch of 2 and a vertical shift of 1. So it's probably going to be smart to do these in phases. So I would start with the 3x. So I'm going to say what I just said. That we have a horizontal compression of 1/3. But visually, what's happening then is that we are, excuse me, in the table of values, we're going to end up taking a third of the inputs, but having the same outputs. For right now, this isn't the true G of X, but I'm going to label it G of X because it's developing. All right. So instead of 6, it's going to be a third of 6, which is 2, dividing by 3. and it's still going to have the same output. Instead of 12, that's going to be 4. That's 18 is now going to become 6, and 24 is going to be 8. All right, so that was nice. They give us nice numbers to do that. Okay, now let's work at the vertical stretch, the fact that they're multiplying by 2. So that's a, vertical stretch of 2. So what that's going to do is that's going to take the output values. Oops, oh, I did not give myself enough space. That's all right. Output values, and it's going to double them. I should have given myself more space. Let's go ahead and shift this then. I'm going to shift this over. I know it's going to take the moment, but it's all right. X, G of X. Okay. Keep making that too long. Okay, so here, sorry, it was 2, 4, 6, and 8. All right. Just going to shift it over. I apologize. So now let's do the vertical stretch. I'll do it right next to it. So the vertical stretch, that's the horizontal compression of 1/3. So now the vertical stretch of 2 is going to look like this. So now it's taking and affecting, the output values. Still referring to G of X here. So same inputs, but this time the outputs are going to multiply by 2. So that's going to be 20 and 28 and 30 and 34. Okay, then the last that we're shifting everything up 1. So it's also going to have a vertical shift of up 1. So I'll squeeze that in. Ooh, let's see, how about we'll do it below. So the final one, a vertical shift up 1. So again, that's going to affect the output values. So the input values are going to still be 2, 4, 6, 8. That's not going to change now once we did the first one. But the outputs are now going to be 1 higher. So 21, 29, 31, and 35. So this down here, that's the final answer when we have done the 3 shifts or transformations on our function there. Sorry to squeeze it in like that. Didn't plan it very well. Okay, so now this is a graph that has been transformed. And we want to figure out what an equation for this graph would be. So first, I'm noticing that it's a U shape, which is a parabola. Know that my base function is x squared. So I'm starting with x squared. And I'm making changes on x squared to get to this. So first thing I notice is that it's upside down, right? So that's going to be a negative in front of the x squared. Now, x squared, just to kind of refresh my memory here, right? Starts at 0, 0, and then it goes 1, 1, negative 1, 1, and then 2, 4, and negative 2, 4. Okay, so it looks like that's the basic x squared graph. So this one, if it's flipped, first of all, it looks like it's been shifted as well. So let's start with that. Let's move it. So it moved left 3 and up 1. So left 3 then is going to be I'm sorry, right 3. I said left 3 and that's right. Wow, right 3. I'm having trouble today. Need more coffee. So that's going to be -3 then, because it's moving to the right next to the x. And then the shift up 1 is going to be a +1 on the outside. Okay, so that's what we have so far. But now I need to see if there's been any sort of stretching or compressing. So normally it would go out 1, down 1 for compression, but it didn't. It's going out 1, down 2 on both sides. And then it's going out 2 and then down. Well, I don't even know where it's hitting. Okay, it's going quite a bit down. So it's a stretched version, which means it looks like the output output values are doubling. So I'm also going to throw a 2 out here with that negative because it's stretching and making the outputs double in value. So I'm assuming then it would have gone to 8 if I had had enough of graph to show. And I can double check to make sure, like I can plug a value in to see if it works. So in my equation here, let me just plug in 4. Oops, I freaking tell it to change color and it doesn't want to. There we go. All right, -2. So 4 minus 3 squared plus 1. All right, so 4 minus 3 is a 1. 1 squared is still 1. Times -2 is -2. Plus 1 is -1. And, ooh, cool, that's what I got out. At 4, it is a 1, -1. So this graph or equation is going to give us that graph. Let me go ahead and box it. And there we go.